So now we need to try for the pi bond similarly, like we did molecular orbital for the sigma ones. Now we'll try the same bonding and anti-bonding for where the pi bond is formed. As you all know that when we want to form a pi bond, there should be a sidewise overlapping. That means their internuclear axis should be parallel. So here I have a 2p orbital and this is my again 2p. So as you can see, their internuclear axis is parallel. Their internuclear axis is parallel. So that means they can try the sidewise combination. So here what they are doing, they are just overlapping sidewise. They are just overlapping sidewise. So now it is an additive one. I need to add the wave function, and we know that when we are adding the atomic orbitals, we get the bonding molecular orbital. So that means I need to add up the overlapping region. So what as a result I get? I get a saucer type shape or an electron cloud above the plane, a saucer type shape and electron cloud down the plane. Right. So this is my plane and these are my electron clouds as a result of addition. And similarly, like what will be the name? It is a pi bond definitely, 2p, and it is a bonding molecular orbital. Right. Now let's try out when we just subtract the electron clouds. So this is my atomic orbital again, parallel internuclear axis. So that means they can show a sidewise overlapping, or we can say they can form the pi bond. So now this is my overlapping region, I need to subtract them, right. So when I'll subtract them, there will be more repulsion and they will repel like this, and this area will create my node. This area will create my node where the repulsion is maximum and where the probability of finding the electron is absolutely 0. And how I need to designate this kind of electron cloud? Obviously a sidewise overlap, so that means pi, 2p indicates the negative one, the wave function is just being subtracted. So it is my anti-bonding, so I need to put an asterisk sign and it will be pronounced as pi 2p star. So if I compare the energies of pi 2p and pi 2p star, so obviously it is going to be same as we did before. That means the bonding molecular orbital is always going to possess the less energy because there is an attraction. Again and again I am telling you that when there is an attraction, there is the less energy, and less energy something corresponds to a state of maximum stability. So that means here again it has a lower energy and more stability, and it has comparatively high energy and less stability. So likewise I think you know that how to draw these figures. Simply you just don't get confused, like there is only a simple type that, like in case of atomic orbital we were drawing the shape of the orbital, but here the molecule is formed, right. Molecule is formed as a result of combination of atomic orbitals. So now the electrons are not under the influence of atomic orbitals, they are actually under the you can say in the molecular orbital. And in the molecular orbital there can be more than one nuclei. Obviously there will be more than one nuclei because atomic orbital is separate as a one piece, right. So it has one nucleus and its electron. But when atoms combine, so their both nucleus are there, like if two atoms combine, so they will possess two nuclei. So that means the electrons in the orbitals are under the influence of more than one nuclei. And how many nuclei? It depends upon the number of atomic orbitals. And second thing, keep in mind that number of molecular orbital formed is always equal to the number of atomic orbitals that combine. Like if 3 atomic orbitals will combine, it will result in the formation of 3 molecular orbitals. If the 4 atomic orbitals combine, it will result in the formation of the 4 molecular orbital. Here we actually obey the law of conservation of this thing, orbital, right. So that means the number of orbitals are not going to subtract, number of orbitals are not going to increase, they will be equal in number. Like the number of atomic orbitals that combine will be just equal to the number of molecular orbitals which are newly formed, right. The difference lies only is that here there was an atomic orbital and here there is more than one nuclei, so we say it is a molecular orbital. By otherwise the you can say the order of filling the orbitals or the subshells are exactly same. We will be obeying the same rules, same Aufbau principle, same Hund's rule, same Pauli's exclusive principle, nothing is going to change, right. But you need to remember this also, this is a very important factor, that in case of atomic orbitals we didn't have any different kind of orbitals, we had only one kind of orbital, right. But here you can say that the wave functions, because 2 atomic orbitals are combining, so that means their wave actually may add up or may subtract up, we are not aware, right. So but we can get either of two, either the result by adding the wave function, or either we can get the result by subtracting the wave function. And for that we draw this thing, I made you draw this figures because it will result in a formation of 2 orbitals bonding as well as antibonding. So just you have to keep in mind the sigma and pi remain same, end to end overlap, head to head overlap, sidewise overlap, everything same. Even the combinations are same, like S and S can form a sigma bond, they cannot form a pi bond. So similar thing happen in this case only. The difference lies only in whether we are adding the wave function or whether we are subtracting the wave function. That's it, right? So just try it out, and you'll be well versed once you'll see this, and once you'll try in your copies, you'll be able to make these diagrams easily, right?